Hello everyone, and welcome to a Valentine's Day special, where we will be calculating the probability that a crush can will fall over due to quantum tunneling, and then how many years that will take. It's going to take a very long time, but yeah, this should be fun. So let's start. A few assumptions to begin. We're going to assume that our little crush can right here is just a cylinder, and also that it has a mass of 400 grams, which is just 0.4 kilograms. Its height is 0.123 meters, and that its radius is just 0.033 meters as well. You can just kind of Google those and convert to the appropriate units. We love Google. Anyway. As before, to actually calculate this probability, we're going to be using the WKT approximation as before. So our probability that this will actually fall over is just asymptotically proportional to e to the minus 2 gamma. And our gamma, as before, is just going to be equal to 1 over h bar times our integral from 0. But this time, instead of having kind of a very large bound, we're actually going to have something that depends on the dimensions of our can. So this is going to be the critical point, basically, where the minimum potential energy we have to put in, more or less, to make the can tip over, or how much higher the can has to be above its center to fall over, I should say. That's what it is. So it's the square root of the radius squared plus our height squared over 4 minus our height over 2. That's just our upper bound, and then again we're just going to have the absolute value of our momentum with respect to x, which is just the same thing as the square root of 2m, and then we're going to have our energy minus our potential energy. But for the purposes of this video, we're just going to assume that we're not giving this can a push of any sorts. We're just kind of letting it stand there and watching trying to see if it falls over. And if it does, I think that would be very concerning, but we're going to watch anyway. So we're assuming E is 0, meaning that we're just left with our V. And our potential energy is just going to be our gravitational potential energy, which is just going to be mg times our height of the center of mass. So just mgx. It's going to be times mgx. So yes, this is actually not a bad integral to evaluate at all. I'm just going to pull the 2m out, or square root of 2m squared g out, to get us m times the square root of 2g divided by h bar, times our integral of just the square root of x dx. For brevity, I'm just going to not write the bounds. And this is just going to be the same thing, actually evaluating this integral as 2m times square root of 2g over h bar. And then times our upper bound right here, which is our r squared, plus h squared over 4, and that's all in the square root, minus our h over 2 to the 3/2. And that's just by integration. So this is our gamma right here. And our gamma is just equal to 9.3, that's a 2, 9.3 times 10 to the 31, which is quite large, as you would expect, because the probability of this actually falling over is quite low. So to actually calculate this probability, we're going to have e to the minus 2 times 9.3 times 10 to the 31. And just putting this in base 10, this does just give us 10 to the minus 8.1 times 10 to the 31. I.e., not likely at all. But that's okay, it's fun. So the second thing we're going to do actually is take this gamma right here. So take this gamma and then try to calculate about how many years we would expect this to happen. So like the half-life, if you would kind of want to think of it that way. So our half-life tau is just going to be equal to 2 times our radius divided by kind of the velocity, of the particles in our can times e to the 2 gamma. Now e to the 2 gamma we've already evaluated. It's just this bit right here, except the minus sign is just gonna be a plus, so that's no problem. The only thing that's different is going to be this v bit right here, because the r is just going to be the radius of our can, which we've already found to be 0.033 meters. So to find this velocity, we're going to kind of exploit some things from like thermodynamics. I really want to learn more about it, but my knowledge is quite limited at the moment. So basically what we know is that we have our kinetic energy, so 1/2 mv squared. It's just going to be equal to 1/2 times our Boltzmann constant times our temperature. So we can just solve for our velocity, can't we? So v then is equal to, well, the halves cancel, don't they? Kb, so our Boltzmann constant times our temperature over our mass. Now we already know our mass, but we're just going to assume this is at room temperature. So our temperatures can be like 298 Kelvin. That's just room temperature. And then our Boltzmann constant is just defined to be 1.381 times 10 to the minus 23. And this right here is actually just going to leave us with a value of v4 of 1.01 times 10 to the minus 10. So we can just plug that in to our equation, can't we? Leaving us with equals, so this bit right here is just going to be equal to, with everything plugged in, let's see, 6.5 times 10 to the, oh no, Decimus didn't write it, oh no, why'd you do that to me, Decimus? 1 times 10 to the 8, and then we already know what our e to the minus gamma is, so we have R10 to the 8.1 times 10 to the 31. So this is how many seconds it would take for the can to fall over. But say we want this in, I don't know, say we want this in years, right? What we do then is just take this and then divide it by how many seconds are in a year, which, well, we know that. It's just 31,536,000. So we just need to, divide it by that to obtain how many years it's going to take for a crush can to fall over. Is about 21 times 10 to the 8.1 times 10 to the 31 years. Not anytime soon, unfortunately, but if it ever does happen, I would recommend buying a lottery ticket, as per usual. And maybe another crush as well, see if it happens again. Anyway, I hope you all enjoyed this kind of short Valentine's Day special. And yeah, I'll see you all in the next one.